It is always a good idea to illustrate our more general considerations with a very simple example. And in quantum information science, when we talk about a simple example, we always talk about a qubit. So let me show you a very simple quantum channel that is probably the most popular channel, known as the depolarizing channel. The name will be explained in a moment when we look at the Bloch vector interpretation of the evolution. So the good thing about qubit, of course, is that we can have this graphical illustration. We can think about states of the qubit in terms of the Bloch sphere, and we can see modifications of the Bloch sphere that gives us some kind of illustration how the qubit evolves. So in the depolarizing model, we assume that the qubit is prepared in some state psi, the environment is in some state E, and the joint system of the qubit and the environment evolves into a superpositions where we assume that the states of the environment form an orthonormal basis. And you can see here the state of the qubit is either not affected at all, so you apply the identity to it, or it is modified by one of the three Pauli operators, x, y, and z. So you can think about this kind of evolution as the evolution when one of the four things can happen to the qubit, namely when the qubit goes through the interactions with the environment with probability 1 minus p, nothing happens to the qubit. And with probability p over 3, the qubit can experience either the bit flip, that is the Pauli operator x, or both bit and phase flip, that's the Pauli operator y, or the phase flip. So this happens with probability 1 minus p, and each of the flips here happens with probability p over 3. So now when we trace over the environment here, we will get the evolution of the density operator, which we can write in the Kraus form, essentially. So that's rho will evolve now into 1 minus p. Let me write it as identity, rho identity, plus p over 3. And here I will have x rho x, the bit flip term, y rho y, both the bit flip and the phase flip term, plus z rho z, the phase flip term. So now it's almost in the Kraus form, but if you want to be really pedantic and want to define the Kraus operator for this evolution, that you can say that, well, we have the Kraus operator E1 corresponding to this term here will be square root of 1 minus p identity, and the other Pauli operators will be proportional, so the other Kraus operators will be proportional to the Pauli operators. So E2 will be equal to square root from p over 3, x, E3 will be equal to square root p over 3y, and E4 is equal to square root p over 3z. So this is actually also consistent with this expression here. As you can see, we can simply rewrite this expression now as E1 applied to psi, E2, E3, and E4 applied to state psi with the corresponding state of the environment E2, E3, and E4. So the evolution, this evolution here, can be written as sum over k from 1 to 4 ek rho ek dagger. So we have explicitly we have expressed this explicitly in the Kraus representation. And you can of course also check that we have the completeness relation, so sum over k, ek dagger ek is equal to, so you can just see that you will have the first term would be 1 minus p identity plus E2, E3 and E4 will give you, well, we have term p over 3 x squared plus y squared plus z squared. So remember the Pauli operator Hermitian, and they square to the identity, so this will be all equal to the identity as it should be. Now the interesting thing is, as I mentioned, once we have a qubit, we can also think about this evolution in terms of the evolution of the Bloch vector. So you may visualize the initial state of the qubit as a Bloch vector pointing in some direction here. And when we do the calculations, when we parameterize our initial density operator in terms of the Bloch vector, so remember that we can always write any density operator of the qubit as 1 over 2 identity plus the Bloch vector dot product with the Pauli operators. Now when we then express this in terms of the Pauli operator and apply this particular evolution, we will see that the evolution of the Bloch vector S is actually quite simple. So S is contracted by the factor 1 minus 4 over 3 times p, the original vector. So this is our new vector, our new Bloch vector S prime. So what you have here at the output is a new Bloch vector S prime, which is contracted by the factor 1 minus 4 over 3 p s. So as you see that as we increase p, so that it is less likely that the state will be preserved, it's more likely that it will be flipped. So if p goes from 0 to some critical value 3 over 4, so for p equal 3 over 4, the whole Bloch sphere collapses to deflates to the point. So the Bloch vector has length equal to 0, right? This factor is equal to 0. But it can even go further, right? So if we take p equal 1, so that means that we only do the flipping. So the environment does the flipping to the qubit. So then the state of the qubit could go to minus the Bloch vector multiplied by the factor, well, it will be like 1/3 of the original length, right? So if we put p equal to 1, then we'll have minus 1 over 3 in front of this expression. So you can even flip the Bloch vector a little bit, so it will be just pointing in the other direction. And it's a good question to ask is, you know, can it go further? Why is it only flipped and extended in the other direction by 1/3 of the original length? Why couldn't it just be completely flipped, regardless which direction it's pointing? Well, that's actually an interesting subtle point that we are going to address in a moment. And that's related to the notion of complete positivity. But here is a simple example of the Kraus decomposition of a qubit interacting with the environment. We remove the environment, then we have the evolution of the qubits. You can see that we have only 4 Kraus operators. We know that for 2-dimensional systems we need at most 4 Kraus operators to express any dynamics of the qubit in this particular case. And there's a very simple and very nice visualization of this evolution. So the polarizing channel is reducing, is sort of compressing the Bloch sphere to 0, and then flips it, and even just it can go further if we just keep increasing this parameter p. So it really depends what is the value of the p, but it will completely depolarize. So you lose all information about the original state for this critical value of p equal 3/4. At this point, whatever you had at your input becomes a totally mixed state. So you just deflate the Bloch sphere into the point.